Welcome back for this week's last lesson from home video. And then next week you'll have spring break and we'll be back after spring break. We start off with a green science article. There's nothing to complete, but it is a really interesting thing to read about light pollution. So this talks about, I'll just read it through with you guys. The light used to keep this road safe at night actually contributes to light pollution. And you guys can see it better in your book or online. But this image behind is the world, and it was created using data gathered by satellites, and it shows light pollution generated by human populations around the world. So anywhere where we have electric lights, that's where you can see. Imagine trying to sleep in a house where light is shining in your bedroom windows at night from in a form of light pollution. It's very difficult to sleep with the lights on. Litter on the road, vehicle exhaust in the air, and fertilizer in the rivers, water are all types of pollution. But did you know that light can also be considered pollution? Light pollution is a problem in many urban areas worldwide. Urban means where there's people living. Artificial lighting can be very useful. It can help keep areas free from crime and allow people to work and drive safely after dark. However, the light that people use often shine out into surrounding areas or up into the night sky, and this is called light pollution. Light pollution is a term that refers to negative effects of artificial lighting. For example, light pollution can disrupt the daily cycles of nocturnal animals. Also, light that escapes into the atmosphere is wasted energy. It's got to go somewhere. In some areas, observing the night sky is very difficult because of light pollution. Awareness of light pollution is increasing. Groups such as the American Medical Association, also known as the AMA, have recognized the negative impact of light pollution. The AMA has passed resolutions advocating energy efficient, fully shielded street light design. The structure of these lights are designed to reduce light pollution. Individuals can take steps to decrease light pollution by carefully choosing outdoor lights with light pollution reduction in mind. So just when you're at home, just kind of observe the night sky near your home. Can you see the stars? And maybe discuss what light pollution in your area might compare to light pollution in other parts of the country. All right, the end of our lesson is upon us, and we're over here in lesson review. This is page 82 in your book. You do need to go back and review everything that we've learned this lesson. So you're going to restate each term in your words below, in your own words below. But you can go back and use your foldable here. You know, it has all those vocabulary words. Use your classroom to find an example. Obviously, you're not in your classroom. You do need to draw a model of that light ray and circle whether it's going to be reflected, transmitted, or absorbed. And remember way back when we had our other foldable here, which talks about reflection, absorption, and transmission. This is a great resource to review what reflection and absorption and transmission all look like. Now, even though this has to do with mechanical waves, it's still, as we read earlier this week, that it still applies to light waves as well. So transparent, what does this mean? What's happening with how much light passes through something? Okay, and give you some more information about that. You can write or draw a model, and you're going to circle, is this reflected light? Is this transmitted, or is it absorbed? Or could it be more than one? You can do 1, 2, or maybe all 3. You tell me. Opaque, how much light passes through something? Is it reflected, transmitted, or absorbed? Translucent, how much light passes through something? Is it reflected, transmitted, or absorbed? And don't forget to draw a model for each of those. Okay, go over to 3D thinking. So we have a model of the electromagnetic spectrum showing that they kind of switched it around on us because on your picture, radio waves was on the other side and gamma rays, it was like flipped over. So in this picture, you've got radio waves over here, which is the lowest frequency. And as you move to microwaves, infrared light, ultraviolet, X-rays, and gamma rays, the frequency increases. But as we stated in the last unit, that as frequency increases, the wavelength decreases. So we've got the distance between is going to be opposite of frequency. So what pattern best describes the relationship between wavelength and frequency? So we've got frequency increasing this way and wavelength increasing that way. Then we move on to reading this passage for number 3. Stars and other objects in the universe give off or emit energy in the form of waves. Most stars emit energy in all wavelengths, but how much of each wavelength they emit depends on their temperatures. Hot stars emit mostly shorter waves and with higher energy, such as X-rays or gamma rays and ultraviolet rays. Cool stars emit mostly longer waves with lower energy, such as infrared waves and radio waves. The sun has a medium temperature range. It emits much of its energy as visible light. These waves travel through vast regions of space and reach Earth. So which of these statements do you think best supports this passage? Is it that the higher the temperature of a star, the more energy it emits? The cool stars do not produce radio waves? Visible light only comes from the sun? The amplitude of a wave, light wave, is determined by its energy. Which one has to do with this passage right here? And I want to remind you guys, I've also posted Learn Smart questions. Go through these before the quiz tomorrow or whenever you're going to take it this weekend. This is great practice to help review questions and help you look up ones you may have missed or ones you might have certain. But this is posted in McGraw-Hill. Learn Smart. Okay, finally, we've got RealWorld Connections here. There's a model here. You want to draw a model. Say you're you turn on a light in a dark room and you see a chair. So I want you to sketch the path that the light wave has to travel and able for you to see the chair. Now, I drew a person, hopefully you can draw a better person, a chair, and a light, but you have to draw the path that the light wave takes. Okay, so you're going to draw some arrows about where the light is going, how it's reaching, going from the light source to your eyes. How does it get there? You have been, and basically, how can you see this chair? That's the key, is how do you see that chair? Okay. You've been asked to help design a new media room. The criteria for the room includes shades that do not let in light from the outside, and they're non-reflective. So what properties should this material for the shades have? So why don't you keep in mind what color should the shades be if you want no light from the outside and it's not reflective? What should the material be made out of? Okay. Finally, we would need to do 2 last things. We're going to revisit the probe on page 65, where you agreed or disagreed with a statement, and we're going to revisit our claim and see if we can now explain using evidence that supports our claim on page 69. So we're going to quickly go back to page 65 first, and then page 69, okay, in our books, and then we will be finished for this lesson. So on page 65, this was our probe. You should have completed the I used to think this, but hopefully not at the end of the lesson you have. But now I know. What do you now know about how sound and light waves move? And then finally, page 69. Okay, we're going to revise our claim. Okay, you look back at your claim. Light is similar and different from mechanical waves. So I want you to tell me how it's similar and how it's different. And then you need to go down here and give me some evidence. Make sure you're doing 3 to 5 complete sentences. Use evidence from our labs, from our notes, from your foldable, and go ahead and write that right here, 3 to 5 sentences. Now explaining how you know that light is similar to mechanical waves such as sound and how light is different from mechanical waves like sound. All right, thank you guys. That is light. That is our unit on light, and I hope you guys had fun learning about light this week. And don't forget, I will be posting the lesson check quiz tomorrow, so make sure you take that sometime. Take your time, you can use your notes, and I hope you guys have a great spring break. Enjoy your time off, and I'll see you again in April.